Hello, everybody. My name is Damian Lopez, and today I'm excited to be talking about climate indicators from terrestrial fauna in the Texas Edwards Plateau, the Rocky Mountains, and near Oceania. I will present terrestrial fauna as valuable records of climate change in the following presentation. My inquiry into the subject will focus on the three specified regions: North America during the late Pleistocene, Western North America during the Cretaceous period, and near Oceania during the Pleistocene-Holocene transition. Through the study of fossil evidence, ancient DNA, and isotope analysis, I show how scientists draw upon these various records to reconstruct past climates and understand the profound impacts on biodiversity and ecosystems. Furthermore, I will be connecting such findings to the current climate in each region and emphasizing what future risks will be posed by human-driven climate change. To start off, it's important to understand why analyzing terrestrial fauna of different geological time periods plays such a crucial role in understanding what our Earth's climate was looking like in the past. With so many species that have now gone extinct or survived the test of time, there is no doubt that they had to play through some serious events over the millions of years until present day. Terrestrial fauna are vital indicators of past climatic states through fossil records, migration, and extinction. Historical climates can be identified by studying such records, and probable responses of species to current and future climate stressors are forecast. In regard to elucidating the history of the climate-biodiversity relationship, past climatic events set the key for interpreting the present changes and devising appropriate strategies for future conservation. In today's world, Texas Edwards Plateau, where Halls Cave is located, experiences a semi-arid climate with mild winters and hot summers. The region's biodiversity today consists of grasslands, open woodlands, and a diverse mix of fauna. However, during the late Pleistocene epoch, during the Younger Dryas, North America saw dramatic cooling, which resulted in a sharp decline in animal diversity. The cold temperatures disrupted ecosystems, forcing many species to migrate or face extinction. With Hall's Cave being a graveyard for ancient mammals, researchers, using a bone and sediment sample from collections across various strata, otherwise known as bulk bone metabarcoding, were able to extract ancient DNA. DNA metabarcoding revealed 100 vertebrate species and 45 plants. Hence, the study could map the change in biodiversity through cooling and warming periods as well as the effects of glaciation. The work by Searshelm investigating Hall's Cave, for example, shows a striking loss of vertebrate diversity during the Younger Dryas cooling event. The large-bodied animals, such as bison and deer, become extinct at the end of the Pleistocene. Plant diversity recovered in the early Holocene, but animal diversity did not, as revealed by DNA analysis. During the shift is graphed in figures from the study. Figure 3 displays the precipitous decline of large mammals, while Figure 4 reflects plant species readjusting accordingly during the same time period. Based on climatic and species distribution analysis, climate scientists estimated that during the last glacial maximum, 20,000 years ago, Central Texas was less than 10.6 degrees Celsius because cold-tolerant species such as the northern grasshopper mouse and white-tailed jackrabbit were able to live there. With Holocene warming over 5,000 years ago, warmer species such as the Mearns grasshopper mouse and cotton rat migrated into the region, indicated that mean annual temperatures by this time had already risen above 11 degrees Celsius. The second region of interest is the Rocky Mountains during the Cretaceous period. The Cretaceous period was one of the hottest in Earth's history, with global temperatures exceeding 30 degrees Celsius. During this time, the shifting of tectonic plates and the uplift of the North American Cordillera led to the emergence of new ecosystems, fostering a significant burst of diversification known as the Cretaceous Terrestrial Revolution. The research conducted by Weaver on late Cretaceous fossil records in the Rocky Mountains revealed that these tectonic processes were crucial for the rise of mammalian and angiosperm biodiversity. The study revealed that the uplift created new habitats, facilitating the rapid diversification of mammals and flowering plants during the Cretaceous thermal maximum, which was approximately 100 to 75 million years ago. By combining fossil data with geological records of tectonic activity, Weaver demonstrated a clear link between increased tectonic events and spikes in biodiversity, illustrating how landscape changes promoted evolutionary adaptation. Ultimately, the interplay of warm temperatures and tectonic uplift significantly enhanced by species diversity, as the altered landscape provided new habitats that support a variety of life. Figure 5 shows the relative species richness of major mammalian groups in the top right and where those mammal units assembled in the yellow polygons. The Bismarck Archipelago, northeast of New Guinea, is made up of hundreds of islands, the largest being New Britain, New Ireland, and Manus. During the LGM, last glacial maximum, stable yet dry conditions in the region gave way to the wetter Holocene climate, and thus an expansion of tropical forests. This provided a further opportunity for the continued adaptation of animal and human populations, especially hunter-gatherer groups, towards these expanding rainforests for tr- towards these expanding rainforests. For tracing changes in vegetation and rainfall over thousands of years, and thus reconstructing habitat transformations of the region, Robert, in his 2023 article, used analyses of stable carbon and oxygen isotopes of fossilized mammal teeth. To ensure accuracy, the teeth were cleaned with aluminum sandblasting, sectioned, and had enamel powder purified for analysis. This process had shown how these changes in climate affected the local ecology, where small mammals stayed in these transformed habitats. On the other hand, human populations expanded their exploitation of these regions and probably extended their social networks. Figures in the study, like Figure 6 below, above, illustrates both the methods and details in greater depth concerning the teeth analysis. Figure 7 then shows localized trends in mammal responses to this changing climate, reinforcing the broader ecological and cultural impacts of these transformations. The climate change in these three regions serves as an important document on the great impact of past climate fluctuations and on the relevance to understanding future risks. In North America, cooling events in the Younger Dryas erased large mammals such as bison and deer. According to Searsholm, today's warmth brings similar threats through habitat loss and droughts. Tectonic uplift during the Cretaceous in Western North America made ecological niches that maintain biodiversity. But now, those same rising temperatures and melting glaciers threaten to be destructive to those systems rather than creating opportunities for speciation. Overwatering in tropical forests near Oceania, which expanded following the last glacial maximum, now risks rising sea level tides, deforestation, and extreme weather. So Leclerc points out these are regions that indicate the habitat loss, species extinction, and displacement due to the human-induced climate change, in case there are no major mitigation effects. This emphasis emphasizes the lessons from historical patterns are important to the preparation of future challenges. Thank you for listening.